So if we put some context to this, for a long time you had scientists trying to explain things. There was a scientist. Put yourself back in the shoes from a couple hundred years ago, and think about what human beings understood. Uh, and one of the things that was of the utmost curiosity, or that people were most curious about, were the stars, the space. What is it? And you guys all took classes where you studied uh, that at one point people thought the Earth was the center of the universe, and that the stars were just fixed things in the sky and all this stuff. And then there were some smart people who figured out, like this guy Kepler and Copernicus and some other really, dedicated scientists that sort of figured out, or at least had a good theory on, for how the Earth and the sun and the moon and the stars, how they were all really acting on each other. But the fact is, no one could mathematically prove it or describe it. And so this kind of pushed a lot of scientists to come up with the correct way of describing the planets in their motion. And it took this new idea of gravity, and what is gravity? And what is speed? What is velocity? And so really what motivated these ideas was among other things, trying to understand something just like that. Why is the moon here? Why is that star there? Why is that planet there? Why do they move? And long story short, that is one of the motivating factors that led lots of people to sort of come up with a new way of describing things, which Newton eventually formalized into what we now call calculus. And calculus is the branch of math that studies change. And so anything that's changing can be described in the language of calculus. Now, what Newton realized is how this change is sort of everywhere in our world, and that it obeys certain simple theoretical laws. And so he formulates three of them. And the second law is this guy right here. So I don't want to like push over things. I want you guys to understand what we're getting at. So homework number 2, ask about Newton's 3 laws. So the second is really often written in an algebraic form. It's that the force on an object is always equal to the mass times its acceleration. Now, before calculus was invented, this equation makes no sense, and let me explain why. Think of it this way. Every one of you, I'm going to assume, has been in a car before, right? You've most likely all have driven, and you've all probably looked at your speedometer from one point to the next. But if I asked you to define velocity, an actual definition of velocity, most of you couldn't do it. And that's not because you're stupid or not smart or you're uneducated. It's because to describe velocity, the definition of velocity requires more sophisticated ideas. It requires calculus. And if I asked you to define acceleration, you couldn't do it either, because that definition requires calculus. So what we typically do in a class like this is we don't specifically define velocity. We talk about this thing called average velocity, or perhaps your average acceleration. Because what really happens is, and the way you need to think about this is as follows. Velocity is a way of measuring the change in your displacement. So velocity is a change, it's a rate of change. How does your displacement change over time? Acceleration is also a change. It is the change in your velocity over time. So think about this. When you get in a car and you slam on the gas, the speedometer goes up. And if you hit it real hard and you have a powerful car, what you actually might feel is you being pushed into the seat. That is your acceleration increasing. It's changing. That means your velocity is increasing. When you hit the brake and decelerate, that changes your velocity. So acceleration and velocity are two important ideas that if you want to define properly, you need some more sophisticated math. And it's also a big confusion. You'll notice in problem 3, I said, describe the difference between velocity and speed. Most people think they're the same thing, and they're not. Velocity and speed are two different things. One deals with displacement. The other deals with distance. Okay, so I'm going to say, before I get to these problems that you originally asked about, I'm not blowing you off, but I think it's important that we look at this from this angle. So what I need you to understand right away is that this equation that I have written here, this force equals mass times acceleration, even though it's written as what we call an algebraic equation, if we're studying something that's moving and it's not moving at a constant speed, if its acceleration's changing, like you in a car or a baseball being hit off a bat, or if we're talking about current being pumped into some electric circuit, the only one of those 3 letters that remains the same is the mass of an object. The other 2 can quite possibly be changing. The force can be changing, and the acceleration can be changing. So this equation is actually a loaded equation. It's not so sort of simple as we might think. Okay, now, here's what's badass. From this equation, if you just know a little bit of math, mostly calculus, you can describe the equations of motions for lots of things. So if you look at problem 6, I ain't just making up that equation. That equation, that number 4.9, that number 300, that's not coincidence. It's not made up. That is basically, you can think of it as laws of nature. So let me explain that for a second. There's this guy named Galileo. You maybe heard of him. Some good things, some bad things. What Galileo did do is he was one of the first people to realize how falling objects work. Don't forget, a long time ago, people didn't understand gravity. They didn't know what it was. They just called it God. Right? They had no idea that there was this force called gravity. They had no idea how to quantify it. We now know how to quantify gravity. And one of the reasons we know how is Galileo was this pretty smart dude. And what he figured out is he had this cool experiment. So what he did is he took a long board. and on this board, he put some balls. And he put this board maybe on a slope of maybe an inch or 2. And then he would watch the balls roll down a board. And he would time how far they went. And then he would make the board a little steeper and a little steeper and a little steeper, a little steeper. And eventually he was trying to get this board, this ramp, if you will, as steep as he could and watch the balls roll down it. And what Galileo realized is that the distance traveled of a falling object, so that if you start thinking about the board being vertical, then the objects are really just falling, right? They're not rolling anymore, they're falling. And what Galileo realized, what his experiments were able to deduce, is that the distance traveled by a falling object was proportional to the seconds or the minutes squared, whatever time unit you want to use. So this 4.9 t squared can be, that doesn't just come from someone making it up, that comes from experimental evidence. This equation, height equals negative 4.9 t squared plus 300. You can arrive at this equation one of two ways. You can go outside with a friend and drop things for a couple hours and record all your data and graph your data, and you're going to recognize that your data matches the graph of this function. Now, what was amazing about what Newton figured out is Newton came at it from a theoretical way. Newton said, great, that experiment does work, but look how I can show you why it works. So from Newton's second law and calculus, I'm not going to do it for you because no one's assuming you have calculus, but you can show the equation that describes a falling object. So what is it? Well, the height is always equal to g, which I'll explain in a second, t squared, plus, I'm going to write h sub 0. Where g is gravity, and that is the only force, and h sub 0 is the initial height. So again, and this is, I think it's worth pointing this out because this is what most humans don't ever get to appreciate. Most of us sit in school our whole lives and we take some classes. They force us to learn a shit ton of algebra that we're like, why are we learning all this? You might take a science class here and there, but we're never quite really told where the connection is. And so this is a great example of where the connection is. Scientists and engineers and physicists and whoever can sit around all day long and do experiments. And then they record their data and they try to make decisions based on their data or describe theories based on their data. And that's what Galileo did. Galileo did a bunch of experiments and came up with an equation similar to this. I mean, it was this, it's just he would have written it differently. But what Newton did is Newton said, let's attack the problem from a theoretical way instead of experiments. And so what Newton's idea was, if we have theory and we use and manipulate the correct rules of our new math, we can actually arrive at this equation using symbolic manipulation. And that's really interesting because what that tells us is that the experiment we're doing is happening for a reason. So the math is basically verifying the experiment, or vice versa. You could say the experiment is verifying the math and the physics. I mean, this is essentially what people do for a living even to this day. You know, when I was in graduate school, I spent a lot of time studying these mathematical equations for the brain. Basically, you're studying how neurons work. And there's lots of people that study this. And so there's certain people called experimentalists. They sit around in labs and pump electricity into brain cells, of dead brain cells, of course, and try to understand how the brain worked. There's other neuroscientists who study it from a very theoretical perspective. And then there's the more applied, the more mathematical heavy neuroscientists who say, okay, let's look for the equations that actually predict and describe the experiments. Not that you give a crap, but it's just like this shirt I have on has an equation on it. Big nerd shirt, right? So this equation is called the Black-Scholes equation. A few smart people tried to figure out years ago an equation that best describes how stocks and bonds prices go up and down. And it's a super uber complicated equation. Sometimes it works, sometimes it doesn't. So the role of the math in all of this, even in this problem, is to give us a language to describe the physical theory. And the physical theory and the math combined allow us to verify and predict our experiments. Does that make any sense? I don't know. Maybe I'm getting a little too ahead of myself. But if we come back to this problem of a falling object, again, this equation can be deduced through experiment, but it's also deduced using theory, and that's Newton's laws. Does anybody have a question about this before we get into these specific problems? Oh, I kind of lied. This is technically wrong. Back up. I forgot something important. There's a 1/2 here in front of the G. Excuse me, excuse me, excuse me. Now, so here's an important thing that you should remember, at least for this class. I shouldn't say in this class. Well, you should know it for this class, but so the question you might ask is, okay, I understand that H naught is different for each problem, but what is G? So what is the correct way of saying this? What is the gravitational force? So what is the gravitational force? This is also an acceleration, if you think about Newton's law. So there's two standard units. We might say that it's negative 9.8 meters per second squared, and we might say that gravity is negative 32 feet per second squared. So look at the units. When I was talking about rates of change, look at the units. The units are distance divided by time squared. So now if you look at problem 6, you'll notice where that 4.9 comes from, because half of 9.8 is 4.9. You might also ask, why is there a minus sign? Well, the minus sign is very important because it tells us direction. And that's the key thing that most of us don't get about velocity and speed. Velocity has a direction associated with it. Speed doesn't. If I say I'm driving my car 12 miles an hour, well, that's not as descriptive as I can be. I mean, what direction am I going? Am I going this way? Am I going that way? Am I going this way or that way? So if we're talking about a falling object, what the minus sign represents is that we're thinking about going up as positive and coming down as negative. So the minus sign is assigning direction. And you've seen this before anyhow. You might not remember this, but going back to your earliest days when you learned algebra, you had, as we talked about last class, you had an XY coordinate system. And we always talk about up as being positive, down as being negative, and then right is positive, left is negative. So that is a convention. Does anybody have a question about this? This is so much fun. What better way to spend a Wednesday morning than this? Actually, I can think of lots of better ways. I think. Have a sip of my chemicals. This is so good. Some of you talked. We had one person is it Caitlin, I think, asked the question. That is so nice. All right. Okay. So let's get back to this problem 6. Let's change colors. Let's get our minds right. What color? We'll go with green. So so the height after t seconds is negative 4.9 t squared plus 3 Hondo. And we want to know what is, first off, we want to know what's the height after 3 seconds. So at t equals 3, that means we just plug it in. What is h? H is negative 4.9 times, let's be very careful here, 3 squared plus 300. And of course, it's the year 2020, so why kill ourselves with headaches when we can just go to a calculator? Like the Google search bar will easily compute this for you. Or Desmos will do it. And when you calculate this, what you end up getting is you get 255.9 meters. So after 3 seconds, we've only fallen what? A little over 4 meters, right? Okay, does anybody have a question about this part? I'm guessing not. Okay, then the next thing we want to answer is we want to know how many seconds pass before it hits the ground. So here you have to use a little deductive reasoning. What does it mean to hit the ground, right? So so it hits the ground when h is 0. This means to determine the time, we solve h equals 0. But h, we know, is negative 4.8 t squared plus 300 equals 0. So now we have to solve an equation, one of these quadratic equations. And how do we solve this type of equation? I'll go slowly because I don't know. Why not? You take the 300 to the other side, it becomes negative. You divide both sides by 4.8. And then you take the square root of both sides. And of course, we're going to ignore the negative solution because we don't care about negative time. What do you get? Well, once again, you go to your calculator. By the way, if you think I make an error or something, yell, because it's possible that I make an error. Excuse me. And you get 7.9 seconds, approximately. Notice I'm using units here. I think it's important that you guys always use units, especially since in your line of work, people die if you don't use the right units. Reminds me of a great story that it's more fun to share in person, but what the hell, I'll share it anyhow. So while I'm sharing this story, ponder if you have any questions. When my first kid was born like 5 years ago, well, if you don't have kids, you might not know anything about this, but you know, like they don't really start the birthing process until like you're dilated enough, right? There's some standard dilation before we decide to bring in the squad. Yeah. That's another thing. I always feel bad for the nurses. Most of you are nurses, right? At least you guys get the shit end of the stick. The damn doctor comes in like once or twice, says hi, leaves. All the nurses do all the damn work. Then the doctor comes in right when it's about to come out, and then they leave and they make 300 grand a year. Damn shame, right? Then again, I think they assume all the risk as well. So, but anyhow, we're down there eating. This is like before they got her all juiced up on the meds, and forget what it was, but I go with my father-in-law down to the cafeteria at McGee, and there's all these student nurses in there eating, and my father-in-law's on the phone with his buddy, and he's like, "Oh yeah, they're gonna start pushing soon. She's 10 meters dilated," and all these kids go and they look, right, like 10 meters dilated. It's like a damn skyscraper almost, and it just made me laugh because like as a kid in school, I used to think that units were the dumbest thing ever. I'm a math person. I just care about the numbers. But then you realize, like in science, units matter. It's very, very important. As you guys know, you give someone the wrong dosage, they can be dead. Give you the wrong dosage of electricity in your old pacemaker, dead. Anyhow, units are important. I would encourage you to make sure you're good at converting units. And by the way, I didn't point this out. I know that it's 2020 and you can ask Google to convert any unit on the planet. I get that, convert seconds to minutes, etc. But you should at least know how to do it by hand. Because I got to be honest with you, setting up problems in a class like this, especially the stuff we're going to be doing later, one of the ways that you know you're doing it correctly is if your units match up properly. If so many of us understood how the units, if we understood better, I should say, how the units work, we have a better job of setting up equations properly. It makes these equations more natural than just symbols, as long as you understand the units. Nonetheless, you'll look at this. I didn't have any units at all in the problem. I could have, but I didn't do it. But I did make sure to have them at the end because I was working in seconds. Does anybody have a question about this calculation? All right, so I want to show you the geometric interpretation of this. So what I'm going to do is I'm going to take you to Desmos, because I think this is important. And then I'm going to go to the Desmos, which I showed you guys this Monday. So I'm just going to plug this in. I'm going to plug in, I think I can use H. H equals negative 4.8 T squared plus 3 Honda. Now, when I first do this, you'll notice that it kind of, you don't see it, but that makes sense because we have to change our scale. So if I hit this little wrench up here, I can change my scale. So I'm going to change it here, and then I'm going to go out to here, but then I'm going to change my Y value because I know I'm starting at 300 feet or meters. So what I want you to do is look at this curve. Now, we're going to ignore the negative part. So I'm just going to say T greater than 0. Now, I want you to, what I need you to do is think about how this thing works. One of the big confusions with this when you first see it is you don't want to think about your object as falling in a trajectory. That's not what this is describing. It's not describing its flight path, because this thing's doesn't have a flight path. It drops straight down. But what this shows you is it shows you how it's falling. When the curve is up top, when it's a little flatter up top, that means we're not falling as quickly yet. And as the curve steepens out, that means we start to fall quicker. Uh-oh, my kid's crying. Drama in the O'Grady house. So you'll notice that at time 0, we're at 300 feet. At 3 seconds, which we calculated earlier. Where are we at 3 seconds? At 3 seconds, we're 256, which we calculated earlier. I believe that's what we calculated. And what this tells you as time goes on, we're dropping. And at roughly 7.92 seconds, we are, and I have to zoom in to get a better estimate of it, we hit 0 roughly at 7.91 seconds, as we found out. So it's also very helpful, I think, in learning this if you look at this geometric perspective. Does anybody have a question about this? Comment? Okay, so let's go back. To our problem. So 7.91, good. That matches. And of course, the 255.9 matches. So we're confident that our algebra is correct because we checked it on the graph. And so we might throw a party. Any questions about this problem before we move on to the next one? Okay, so now if we want to talk about 8, we can have an even more general problem. Instead of just thinking about dropping an object straight down, we can introduce another scenario where maybe I throw something straight up in the air. What happens when I throw something in the air? As you guys know, once it leaves my hand, it slowly slows down, it hits a high point and falls back down. So what we want to imagine in this particular problem is we are going to launch a toy rocket into the sky. Okay, so before we do this particular problem, let's note the more general scenario. So we'll call this a fun fact since we ain't going to derive it. So if an object is tossed, whatever you want to say, straight up in the air from a height of h sub 0, its height after t seconds is height. So we have the same first part, minus 1/2 gt squared, and then we also have the plus h sub 0. However, there's a middle piece to this now if we assume that the thing is tossed or thrown down. The middle piece is what we call the velocity component. So here, v sub 0 is its initial velocity. So how hard did I throw it? How fast was my arm moving when it left my hand? So if you look at the problem number 8, I kind of explained this for you. You guys were out there hanging with Sister Candace. What a sight that was. And all the other sisters of the mother house. And you guys like the toy rockets, just like SpaceX did last week. Did any of you watch that Nerd Fest? It's pretty badass, though. All right. So if we do that, and notice I changed my units in this problem. Here we're using feet instead of meters. So in the special case of problem 8, good God, what a time to be alive. In this problem, so for number 8, we have gravity equals negative 32 feet per second squared. We have initial velocity is 200 feet per second. And then we had h sub 0 equal to 75. So that gives us the following equation of motion. We take half of 30 or 32, we get 16. All right, so this problem is almost identical to the one we just did, only there's this missing component. This guy, my rocket's going to start 75 feet in the air, and it's going to shoot up, and it's going to get eventually so high that it loses its war with gravity. And when it loses its war with gravity, it stops and then falls back down to the ground. And what we'd like to know is, first off, where's it at after 5 seconds? Where's its maximum height? And then lastly, when does it hit the ground? Does anybody have a comment or a question before we go through this calculation? All right, so for part A, that is directly straightforward. H at t equals 5, what does H equal? H equals negative 16 times 25 plus 200 times 5 plus 75, and we can spare our headaches with this. We can go right to a calculator to figure all this out. So if I can actually learn how to hit the damn calculator correctly, that would be real nice. bear with me. I'm having technical difficulties. So, whoa. If my calculations are correct, this becomes 675 feet. All right, so bear with me. I'm trying to. All right, so does anybody have a question about that part? Okay, now where's the maximum happen? So before I do that, I want to switch screens. Hopefully you'll follow along with this excitement. And we go back to Desmos. So if you look at this parabola that I've graphed, this is the parabola that we just had. And by the way, I was sharing this, I think it was with you, Ryan, on Monday. If you type in an here, let me show you. Let me just do it from the very beginning. I'm going to use Y's and X's just because Desmos likes those better than X's and T's and that. So if I draw the equation like this, negative 16x squared plus 200x plus 75. And then I don't really care about negative values of the input, so I'm just going to say my input has to be greater than or equal to 0. This is my time. So what you'll notice is if you press this little gear up here, and then this little mini table button, what you can do is you can see the results. So what happens after 1 second? It's at 259 feet. And then 2 seconds, it's at 411. 3 seconds, 531. 4 seconds, it's at 619. 5 seconds, which we just calculated, is at 675 feet. So you don't want to think about the rocket is moving in the sky like this. You want to think about it as it going up and straight down. But this curve tells you how, and think about it from an intuitive standpoint. Its change in height starts to slow down the higher we get. And then eventually at this point, which we need to find out, the top, then it's going to turn around and it's going to start falling down to the earth. And we want to find these 2 points out. We want to know when it's at its highest peak, which it looks like it's 700 feet. How do we find that algebraically, though? And then it looks like it comes back down to the ground at 12.864 seconds. So does anybody have a question about this picture? Now, you could argue, O'Grady, why do we have to solve it by hand? You just showed me how to get the answers. Well, because you should still solve the damn thing by hand. It's a learning experience. But I get your... By that, I like this. Some people are like, why do we do anything if the computer can do it? Well, by that logic, we shouldn't teach shit anymore then, I guess. Oh, I swore. Sorry. All right. So if we go back here, let's do part B. Part B says, find the maximum height. Now, here's a fact you probably don't remember, but we're going to tell you anyhow. The max height occurs at, you might remember this word from your nightmares of algebra, at the vertex of the parabola. So what is the vertex? Well, the vertex is the point now this is going to look real scary. It is when t equals negative b over 2a. So you might say, what's b and a? Well, I'm talking about in general. So what is your b component? Well, if you remember what a quadratic is, this is your A, this is your B, and this is your C. These are the coefficients of your equation. And so if you wanted, you could say, being more specific to this particular problem, where is the vertex? The vertex is, if we erase this B over 2A, we can say that it occurs at negative 200, or in general, we can say negative V naught over 2 times, let's say, let's be more careful. I don't want to say something illegal. Over V naught over 32. So if we take that number, max occurs at T equals 200 over 32. Which simplifies to, what, 25 over 4. So this is 6.25 seconds. So when T equals 6.25, H equals, if you plug it in, H equals 700 feet. And so this is the rocket's max height. The highest it will get is 700 feet. Of course, we saw that when we looked at the graph a few moments ago. Does anybody have a question about this part? Comment. Anything? Going once? All right, so then parts. Right. For part C, we have to solve the equation H equals 0 again. So
What are you taking, Jordan? You have his food.
So it hits the ground when H equals 0. So that's negative 16 t squared plus 200 t plus 75 equals 0. Now look, I don't care if you do this by hand or not. I wouldn't do it by hand. I would use the quadratic formula, calculator, use whatever you want. Using the calculator, it hits the ground when t equals what? Well, you have to go solve that. You can plug these numbers into the quadratic formula. I would encourage that you do that, even if you think it's a fruitless exercise, but you don't have to. And when you get it, you get t equals 12.86 seconds. So this rocket is in the air for almost 13 seconds, is essentially what we're saying. Isn't that fun? Now you can go out, buy a toy rocket from the hobby shop and spend the rest of the green zone and quarantine shooting shit in the air. problem is, and this is something that needs to be pointed out. These equations are actually very accurate, but obviously the windier things are, the less accurate they become, the more humid. If you want more accurate expressions, you have to do some more advanced math. There's this thing called drag and wind resistance that we're not including here. But for the most part, these are pretty accurate. Any questions about this problem? Fun times, huh? I need a sip of the scissor. Let's see how many emails I have today. Oh, 112 this morning. How the hell am I supposed to answer 112 emails? Can anybody answer that to me? No, it's absolutely insane. 112 emails.
Getting it from Mary Jo.
Who's Mary Jo? I don't even know who that is. Is that a joke that I'm supposed to be getting? I don't even know who Mary Jo is. How about this? I get scam update. Oh, people are stealing people's government cheese. What else is new? All right, let's move on to the next fun problem. Okay, so the next problem was number 9, I believe you asked. Okay, so So Newton's laws hold for many things. So such as a spring. So one of the things you study in a basic physics class, and even more, a little more advanced physics classes, is you spend some time with springs. And you guys will think that's stupid. Who the hell cares about a spring, right? But don't forget what a spring is really representing. Much like a pendulum, if you remember what a pendulum is. And the equations for motion of a spring and a pendulum are very much the same. So let's imagine something here. I have some ceiling, and then hanging from the ceiling, I have a spring. So let's make that in blue. So I'm going to be real crappy at drawing a spring, but it's going to look something like this. Right? And then at the bottom of this spring, I have something on it. Like, let's call it, we'll make a little pink circle. This will be our mass. And what you guys, I think, all know from intuitive things, or if you want, go to YouTube and just YouTube or Google spring hanging from a ceiling, physics, is that if you just let that thing sit there, depending on how heavy the mass is, it's going to pull down a little bit, and it's going to be sitting. We call that equilibrium. It's at rest. And what we know from seeing it with our own eyes before, or from actually doing it, is that if I take that mass and I pull it down and let it go, it's going to start oscillating up and down. Now, eventually, it will come to rest, provided gravity's involved and all that. And we can describe, using Newton's laws, exactly how it will oscillate. And this is what we call harmonic motion. And what's fascinating about this is this doesn't apply to just springs. It applies to many, many things that oscillate. Electricity behaves in this way. Current, I should say, being more specific. Maybe I mean, we'll talk more about it later, but you've heard of like AC and DC, not the band, but alternating currents and direct currents. Think about every time you get in a car and drive. Think about an airplane landing. How is it that an airplane can land without bouncing up and down and flying away? Or how is it that you can go over big bumps and hit potholes in your car where you have suspension? And the general idea of how that works is based off of these ideas. So how does a spring work? Well, again, you pull the mass, it oscillates up and down, and we'd like to know, how does it oscillate? What is the equation that tells us where it will be at any given time? So what we like to do is we'll give names to this stuff. We'll call this distance d equals its displacement. And so at time t equals 0, d equals 2 is the rest state. That's one way. Or equilibrium. So that's it. That's just how it hangs. So that's what's happening. It's hanging at a specific distance from the ceiling. So in a particular scenario, now I'm not giving you the details, but what I mean a particular scenario, that means if I have a certain mass, if I have a certain strength to my spring, maybe you've heard of something called Hooke's Law or something before, where you talk about every spring's different. I mean, the spring that you put in your car ain't the same kind of spring that you put in your ice door in your refrigerator. One has to be stronger than the other. You guys know some springs, like a slinky, you can pull real easily. Other springs you couldn't. They all have a different strength. And so depending on all that, those scenarios, we might have d equals the sine of t plus 2. Now here's sine, which is a trig function, which most of you learned about a long, long time ago and have probably since forgotten. But what's beautiful about the trig functions is they're really good at helping us describe things that oscillate, things that move like a spring. So if I pull something up for you in a second here. Looking for, where did it go? I just lost it. So I'm going to hit the wrong button. That's why. Come on, Grady. Slipping in your old age. So I'm going to pull up this screen. So what you should see right now is a yellowish orange page with this little picture. So you might not remember. Let's actually, before we go there, let's go to Desmos for a second. If I graph the function y equals sine of x, here's what the sine looks like. It's called a sine wave. It goes up and then it goes down, and it goes up and it has these nice properties. Now you probably learned about the sine years ago is something to do with angles, right? Opposite over hypotenuse and all that. And that's true. But a better way to think about sines and cosines or to think about you traveling around the circle. I would encourage you to Google sine, circle, or just go to a Wikipedia page for sine and cosine and look at some of the pictures, the GIFs and the little videos to get a better understanding of it. But what's nice is we can think about, this can describe how a spring goes up and down. And this is a good picture of showing it. Right here, I have this spring in equilibrium. And then okay, maybe that's a bad way of thinking about it. Start in the middle. If I pull my mass down, then I'm down here, then it goes up, hits its highest point, then goes back down. And then it'll oscillate like that for a while, and then it'll die out. So this is a good picture for you understanding why the trig functions pop up when we talk about things that oscillate, that go up and down. So if we go back to our homework problem, we want to know when D is as large as it can be. So D is largest when sine of t is largest. So this requires that we know a little bit about the trig functions, and so that's why I put this problem on here. I thought it was a good window for you to maybe review some basic facts. So when is sine its largest? Well, a basic fact of the sine is that it's its largest at pi over 2. That's when it hits 1. So you probably do not remember it. That's okay. That's why I put the problem on there. So the sine evaluated at pi over 2 is equal to 1. That's the largest value the sine ever gets. So if I go back, I hate going back and forth, but it's worth seeing. If I go back to Desmos, look at the largest value that the sine hits. It's at pi over 2, 1. And coincidentally, it hits its minimum value at 3 pi over 2. Now, of course, you would not remember this most likely. That's why I put it on, to remind you. Or to convince you to, for the hell of it, review some trig. So again, yeah, don't get overwhelmed by this problem. This is basically what we wanted you to get out of this. Does this make sense? Does anybody have a question about this particular problem? So what is the maximum distance then? Or the maximum displacement, if you will? So what we can conclude is the following. So we conclude that when t equals pi over 2, and then this is going to be scary, but the sine is periodic. So every 2 pi, it repeats itself. So if I go 2 pi more, so if I went to pi over 2 plus 2 pi, etc., d equals 1 plus 2, which is 3. So this is sort of a loaded problem. It's relying on lots of facts that there's no doubt someone asked you to learn many years ago, and there's also no doubt that if you're human and you haven't used it in 10 years, you have no recollection of it, which is fine. But I thought we would put it on there because it's another example of how Newton's law works, and it also can help you remind you of some basic trigonometric ideas. It's interesting, the functions sine and cosine, excuse me, and those scary stuff we talked about last class, the exponentials and the logs, those guys turn out to be everywhere. They're ubiquitous in math and science and engineering. And they're not something that someone made up to piss off high school students. They're actually very, very important functions, and they do an amazing job at helping us understand the world we live in. So really the hard part for the student, the learner, is, and I tell this to all my classes, is you have to get, you know, so I mean, I'm a math professor, right? So I teach math. I teach freshman level math. I teach like calculus, but I also teach, you know, higher level math. Like this summer, I'm teaching a math neuroscience course. And what we always find in the lower courses, because of experience, and or I should say lack of experience, and this is most likely going to be an issue for many of you, is you have a lack of experience with the language of math, the language of equations. And so what happens is all these symbols that you're very unfamiliar with, they become overwhelming. And those are really the barrier that are preventing you from learning the ideas. It's this mental aspect that you're like, holy hell, how am I supposed to remember all these weird symbols? How am I supposed to make sense of them? And so when you can't make sense of that, when you're fighting the mental battle, that's the hardest part. So, you know, part of the reason I assign problems like this is to not say, hey, look, you're stupid, you don't remember these things. It's for me to sort of kind of do a few different ways of encouraging you to maybe reviewing some stuff, because it might be helpful. So that's just my thought process on that. Does anybody have a question about this problem? I don't know if that makes sense, but again, it wouldn't hurt for you to review some properties of trig functions just because it's useful to know. It's helpful. I think so. That was what, 6, 8, and 9. Does anybody have a question about those 3 problems or Newton's laws? I think those are probably the most difficult problems on this assignment, right? Maybe 12 is a little tricky, but it's not. Those ones require higher level math. I think the rest of everything is basic arithmetic, multiplying and dividing stuff, if I'm not mistaken. Does anybody have a question about any of this stuff? You know, in the past, what I found is you guys understand certain things like barometers and the manometer. I like to call it a manometer. You know, things that you should understand if you're in a hospital room: gauge pressure, absolute pressure. What does all that crap mean? You should have an understanding of that. Now, don't forget, this is a physics class. So, you know, I've had someone ask me in the past, well, why are we doing these falling objects? We're supposed to be talking about physics related to your gig. Well, that's true. Yeah, we're going to talk a lot about gases and fluids and pressures of that. But we still have to do physics. I mean, the name of this course is physics. It's not physics just for anesthesia. It's called, I mean, really, don't forget, this is supposed to be a basic, what we call a survey course in physics. So we're supposed to cover all the fundamental ideas of physics, right? So that's why we're talking about toy rockets getting launched in the air. And that's why we're going to do problems later on that you might deem irrelevant to your career. Look, we're going to ask you to calculate. I mean, look at these syringe problems. Some of these syringe problems are important. As you might already know, you can get different pressures by changing diameters. But some syringe problems we're going to do are kind of like irrelevant. Like you're never going to be, I don't think you're ever going to be giving someone medicine and be wondering to yourself, I wonder how fast the medicine is coming out of the needle. Like, no, you're not going to be thinking that, right? But you'll be able to calculate it once you take this class. But you're never going to be drawing blood and saying, I wonder how fast. Although I guess you could, because you know how quickly it gets into the tube or whatever. So there might be some things that you find irrelevant. And if you do, I apologize for boring you, but we do have to kind of get all physics. So you have that. Does anybody have a comment or question? Are you guys good with the rest of these? If not, let me know. And if you are, then I say we talk again Monday morning. Does anybody want to anything? All right, so what I'll do then, since no one's blabbing, is I'm going to end El Recordo.